Okay, so we're going to compute a contour integral, and the contour that we are going to integrate over is pictured here. So it is a collection of line segments joined together at the edges, and it creates, well, a closed contour, right? So wherever we start, we will have to end at that same spot. And the function we're going to integrate is 1 over z minus I. So I is right here. It's interior. So the domain of our function is actually everywhere except for I. So if we were to try to apply the Cauchy-Goursat theorem, well, we wouldn't be able to because our domain is not simply connected as a whole. So I is, where's black? Let's note that C contains, well, C has the singular point of our function, so the bad point, interior to it. So we can't apply the Cauchy-Goursat theorem. We also don't want to necessarily do this integral because if we were to do this integral, sorry, I should shade outside as well. If we were to do this integral, let's see, our contour is what is it? It's a hexagon, and so we have to do 6 separate integrals, which we could do. None of them are hard, but we'd rather not. So what we're going to do instead is we're going to use the principle of deformation of path, and I'm going to put in purple here. Sorry, I'm not good at picking colors, but in purple, we're going to let C1 be this guy. So what's C1? C1 is going to be the circle of radius 1 centered at I. All right, and we're gonna use the fact that C1 can be deformed into C to see that the integral over C1 of dz over z minus I is the integral over C2 of dz over z minus I. So we can just integrate over C1 instead because it deforms into our original contour. All right, so let's do exactly that. Well, C1 has parameterization. Well, if the center of C1 was at the origin, it would be e to the it, but it's not. It's at I, so we move it. And this is on the time interval from 0 to 2 pi. And so let's go ahead and compute dz real quick. So dz is going to be I e to the it dt. And then therefore the integral over C1 dz over z minus I is going to be the integral from t is 0 to 2 pi I e to the it dt over e to the it plus I minus I. So we plugged in our z in the bottom and our dz up top. Now these guys cancel. I minus I is 0. And so these ones cancel. And so then what we get is, oops, wrong color. What we get is integral from 0 to 2 pi I dt. And this is an integral we've computed already. It's just going to be I times the length of the interval. Now notice how fast that was, up to me explaining what C1 should be. That was very fast. It's much faster than computing 6 separate integrals and then adding them together. And this is how you use the principle of deformation of contours. Makes a lot of these computations simple. In particular, you can reduce a good chunk of the simple closed contour integrals to integrating over an appropriate circle. And when you are integrating over a circle, it's very easy to plug in the parameterization because the parameterization is just like r e to the it plus the center. And that's very helpful.